Hello and welcome back. These would be the notes for 4.1, plot points in a coordinate plane. There is a PDF available if you want to print it out. There are only 6 pages here. First thing I want to talk about is what is a coordinate plane. It's simply a two-dimensional grid formed by two number lines. They intersect perpendicular to each other at 0. The horizontal number line is referred to as the x-axis. So if you look at the graph down here at the bottom, the horizontal line is referred to as the x-axis. And the vertical number line is referred to as the y-axis. The vertical one would be here. And the midpoint right here where they intersect is 0 for both number lines, the x and the y. An ordered pair. In order to plot a point on the plane, you need something called an ordered pair. And it looks like that inside parentheses, separated by a comma, x, y. That would indicate that we need one value for x and one value for y. So if I were to go, let's say, plot a point right here, that point would have an x value and a y value. And if I count out, the x comes first. That point is 1, 2, 3, 4 over on the positive. So that would be 4. And 1, 2, 3 up on the positive y. So that point would be at 4, 3. The x and y axis breaks up the x and y axis breaks the plane into 4 sections called quadrants. The quadrants are numbered 1, 2, 3, and 4. And we start with number 1 in the upper right hand corner, and then we go in a C form or counterclockwise form. 2 would be there, 3 would be here, and 4 would be there. One thing you want to know about the quadrants, or at least the points in them, is you have all positive values on the right hand side of the x-axis, and on the left hand side you have all negative. For y you have all positive up, and down you have all negatives. So what that means is in quadrant 1 you have a positive followed by a positive value for x and y. Whereas in quadrant 2, you will have a negative for x, but you'll still have a positive for y because you're still in the upper section. When you go to quadrant 3, you'll have a negative for x and a negative for y. And when you go to quadrant 4, you will have a positive for x and a negative for y. And that pattern exists all the time, so you might want to remember that pattern: positive, positive, negative, positive, negative, negative, and positive, negative for quadrants 1, 2, 3, and 4. Example 1, naming or locating points on a coordinate plane. We've already named one of them, so let's go over here to A, and we're going to name the coordinates. We're going to count out A for x first. Remember, this is x here and this is y. So to get underneath that point, we have to go positive 3 for A and for x, and for y we have to go positive 2. So that point is located at 3, 2. We're going to do the same thing for B, point B. So I'm going to create my x and y ordered pair. We're going to do x first, which is 1, 2, 3, 4, but this is in the negative direction, so that would be negative 4. And 1, 2, 3, 4, 5, positive 5 for y. So the coordinates for point B would be negative 4, 5, x followed by y. Now we want you to go ahead and plot point C. Point C is x followed by y, alphabetical. The negative 5 for x would be left 1, 2, 3, 4, 5. And then the y coordinate would be down 1, 2, 3. And where those 2 points intersect would be right here. And we call that point C. And sometimes we go ahead and put the coordinates for points on the graph, just like we did here and here. For right now, we're not going to do that. Point D is positive 6, positive 1. So positive 6, 1, 2, 3, 4, 5, 6. And positive 1 would be here. So right here would be point D. And for E, negative 8, 0. So negative 8 for the x would be, I'm going to do this one in red. 1, 2, 3, 4, 5, 6, 7, 8. That's negative 8. And 0 for y would be right at the origin, so we don't go up or down. So our point would be right here, right on the x-axis. And you might notice that anytime we have a 0 in our ordered pair, the point will either be on the x or the y-axis. Well, in this case, it was on the x-axis. So you might notice that the 0 was actually in place of the y value. So that would suggest that anytime you have a 0 for y, you'll be located on the x-axis. What if we had a 0 for x? Chances are, if there's a 0 in there, it's going to be on an axis. But if I have a 0 for x, this point will probably be located on the y-axis. And we'll go ahead and graph that. So 0, 4. So 0 means no left or right movement, but up 1, 2, 3, 4. And our point would be right there. We'll call that point F, and that would be at 0, 4. Example 2, plot points in a coordinate plane. We're going to graph a function, and the function we're going to graph here is y equals 2x minus 1. The first thing you know is that a function is a one-to-one relationship. That means for every input, it matches only one output. So let's go ahead and take a look at what that means. We've got domain, input, and independent. They all mean the same thing as the x-coordinate. That's the one you can pick any number you want for. So in our function, x here is our domain, input, or independent value. So we have one input matching exactly one output. Range, output, and dependent all refer to the y-coordinate. So in our function, our equation, the y value is the y-coordinate is the output. We often refer to it as range. So for every one input, it should only match one output. Keep in mind again that another way of naming input or independent is the words domain. So I'm going to go ahead and select some values for domain. I'm going to select a 0, a 2, a negative 2, and I'll go ahead and pick one more. Let's pick, I'm going to pick 4. Positive 4. And the way we calculate these is we take our domain values and we substitute it in place of x, and we calculate the value of y. So if I put a 0 in place of x, y would equal 2 times 0 minus 1. 2 times 0 is 0, and 0 minus 1 is negative 1. So the range value that matches 0 would be negative 1. And I'm going to go back and change that, make that red. Negative 1. So my next domain value is positive 2. So to calculate my range value that matches that, we substitute a 2 in place of x. That gives us 4 minus 1. So the output, or the range value, would be 3. The next one would be a negative 2 input. Negative 2 in place of x. That gives us negative 4 minus 1. And the output then would be negative 5. I'll do it again for the last one. So y is equal to 2 times 4 minus 1. 2 times 4 is 8. Minus 1 would give us an output of 7. So we can call all these the y values, but we can also refer to them as the range. Just like we can call all these the x values, but we can also refer to them as domain. This is input, this is output. Domain and range are in alphabetical order, x and y are in alphabetical order, I and o, input, output, are in alphabetical order, left to right. Now all we got to do is go graph these points. 0, -1 would be here. 2, 3 would be here. -2, -5. -2, 1, 2, 3, 4, 5 would be here. And 4, 7, be 3, 4, 1, 2, 3, 4, 5, 6, 7 would be here. And one thing you might start to notice is all these points appear to be on one single line. So if I were to draw a straight line, I should be able to draw that straight line all the way through, kind of like that. And I can adjust this a little bit. And as it turns out, that the line itself, the line, represents all possible values of the function. I can select domain values infinitely, which means I can produce range values infinitely. And you'll notice that on the domain side, every time I put in a 0, I will get a -1 out. That's what makes it a one-to-one relationship. Example 3. They give us a table. They want us to explain how you know the table represents a function. So when the table is written in a horizontal fashion, usually the top number is x, that's the input, the bottom number is y. So for each input, we should have only one output matching. So what we do is we kind of scan through here and see, are there any duplicates of my input? We don't see any duplicates, which means we don't care if the output is the same or not, because what we don't want to have is the same number, let's say 12. We don't want it producing a 40 one time and a 12 producing a 35 the next time. If we have that case, then that would not be a function. That would not be a one-to-one relationship. So in this case, it is a function because there are no inputs that are duplicated producing different outputs. Go ahead and graph it, and we do have the graph over here. And we can see that in general, the graph appears to go up and to the right, so it appears that we have a positive trend forming. And another way that we can test to see if we have a function by looking at the graph is to use something called the vertical line test. Okay, so I'm going to draw a line, vertical line. I'm going to use red just to make it easy to see. And then as I run this line across the graph vertically, horizontally I mean, it should not touch more than one point at a time. So as I move it across, it only touches one single value. Okay, even though these two numbers down here, this one and this one, appear to have the same y value, that's okay, as long as the input value is different. So if I were to have a non-function here, let's suppose I have another dot right there, and I were to run my vertical line across it, you'll see that I have, when I cross it like this, I have 2 points that would match that vertical line. So for whatever this value of x is, it would have 1, 2 outputs for y, and that would be not a function. So if I get rid of that extra point, because that was not part of the original graph, we can see that this is a function, and it passes the vertical line test, which is another method of looking at the graph and determining if the graph itself is a function. So as long as you run a vertical line, the vertical line only touches the graph at one point at any given time, that would be a function. We've already talked about the trend. Go ahead and put that trend back in. The trend appears to be up and to the right, so this is saying years before or since 1920, number of votes. So as the years have gone up, if we look at the numbers on this side, the numbers are going up. So as the years go by, the year increases, the number of votes that were casted appear to be increasing also. So if both values increase, we have a positive trend. And a positive trend is something that goes up and to the right. So as one value is getting bigger, the other value is also getting bigger. Example 4, years before or since 1972, and votes again. So we're going to assume that the top one is the let's change that. The input, which is x, and the bottom one is the output, y. Is this a function? We'll look across here, see do you have any duplicates of your input values. Don't have any duplicates, so it should be fine. So is this a function? The answer would be yes. Describe the trend in the number of votes cast. Well, as the years progress, remember they're going in this direction, as those numbers get higher, what's happening to the y values? Are they getting higher or lower, or can you not tell? Well, it appears that they are getting higher also, so the trend would be as the years since, let's write that a little better, 1972 increase, the number of votes cast also increase.